In the last video, we derived the weak form of our boundary value problem from the strong form of our boundary value problem, which modeled beam and beam elements. The form of the weak equation that we derived in the last video is again presented here, now typed. Now, besides being typed, the only difference between this form of the weak form of our boundary value problem is I've moved these four terms that were on the right side of my equation, or left side of my equation, and I moved them to the right side of my equation. Remember, these four terms came from when we used integration by parts twice, and then evaluated what was going on at boundaries. So these four terms represent the embedding of our boundary conditions into our weak form of the equation. Remember, note that this F1 is the external force at node 1, the external moment at node 1, the external force at node 2, and any external force at M2, or node 2. Okay? So now that we have the weak form, if we want to go further in deriving any of these variational calculus-based methods, the next step is to approximate or come up with an approximation for the function we're trying to solve for, v, the displacement in the y direction, and come up with a specific virtual function, which here I'm calling n. All right? Since we're applying Galerkin's method, we're going to use the approximation dictated by the Galerkin's method. We're going to approximate that our v of x is equal to, or approximately equal to, our shape vector, the same shape vector that we derived when we were looking at the principal minimum potential energy method, times our displacement vector. Remember, our displacement vector, u, is just a shorthand way of writing v1, phi1, v2, phi2. Okay? Now, you don't see a whole lot of vx's in this equation. What you do see is the second derivative of v with respect to x. Note that the second derivative of v with respect to x would then just be equal to the derivative of my shape vector, which we previously called our b vector, times our displacement vector, which does not depend on x. Now we know, and we have a substitution for v of x and the second derivative of v with respect to x. Now I need to decide what I'm going to choose for my virtual functions. Well, what Galerkin's method dictates is for the virtual functions is to actually use the shape functions that we originally derived. These are shape functions that we know. In this case, they're simple cubic polynomial functions. I know their value at 0, and I know their value at L. So I can use them as my virtual functions. Remember, I'm calling those shape functions n1, n2, n3, and n4. If I need the second derivative or the first derivative of these shape functions, I know these are just cubic functions. I know how to take the first and the second derivative of those. Remember, we called the second derivative of these functions b1, b2, b3, and b4. Now let's refresh our memory of what these equations look like. This shape vector I present here, where this is n1, n2, n3, and n4. Here, just because it's a little more brief, I'm demonstrating it or showing it as a column vector. However, I could take the transpose of this and get the row vector like I have it here. If I take the derivative of these four functions, I can get these two equations, these two vectors. Here, the first derivative vector, and this vector I called b, where this is b1, b2, b3, and b4. Okay? So now that I have my substitutions, I'm ready to go ahead and put these approximations into this form in order to derive my Galerkin's method-based solution. Okay? So if I go ahead and do that, I'm going to get EI, the integral from 0 to L, make my substitution. That will be the row vector B times the column vector U times a second derivative of my shape functions. Note, however, that I have 4 different virtual functions. So I'm going to do this 4 different times. I'm going to do this first for my first shape function and its derivatives, again for the second shape function and its derivatives, again for the third shape function and its derivative, and again a 4th time for the 4th shape function and its derivatives. So instead of doing this 4 times, I'm just going to write here I want the second derivative of my virtual function with the second derivative with respect to x. I called that b. I'm just going to write b I, again, that's a function of x, dx, all right? And just note that this represents 4 functions, okay? Equals negative the integral from 0 to L wx, note that's a scalar function, times my ni, which again is a scalar function of x just multiplied by another scalar function, dx, and these 4 terms, which are all scalar functions. So this will be plus f1 ni evaluated at 0 minus m1 d ni dx evaluated at x equals 0 minus f2 ni evaluated at L plus M2 dni dx evaluated at x equals L. Now note, each term in this equation, while some of them have vectors in it, remember, this is a row vector times a column vector. This will turn into a scalar function. Likewise, this is a scalar function times a scalar function. This will be a scalar function. Each one of these guys is a scalar function. So this is a single scalar function without any vectors in it. Okay? Note that this u here can also be moved outside. All right? So if I wanted to. All right? So now I can go ahead and I remember this is a scalar function, but there are 4 of them, 1 for each I. So I can stack the 4 equations I get on top of each other, and stacked in the 4 way the 4 equations are stacked up to each other, I can write those 4 equations in this form, where the first equation when I equals 1 is the result of my displacement vector times these 4 terms. It ends up my first equation when wx times n, the first n, will represent my first equation. And why can I write this like this? That comes from the fact that I have 4 terms here. In the first one, when I go through I equals 1, if I look at n1 here, n1 evaluated at 0, I have x equals 0, that term will go to 0, that term will go to 0, this term will not go to 0. I have L cubed over L cubed, that's equal to 1, so this term will be 1. The first derivative of n1 is here, evaluated at 0. This will go to 0. It'll turn out n1 evaluated at L, where I'll have 2L cubed minus 3L cubed plus L cubed will turn out to be 0. Likewise, the first derivative evaluated at L will end up being 0. When I go to N2, when I equals 2, this term will end up being 0. This term will end up being 1. This will be 0. This will be 0. When I equals 3, 0, 0. This will end up being 1. This will end up being 0. When I equals 4, this will be 0. This will be 0. This will be 0. This will be 1. The result of which is if this row represents when I equaled 1, I'm left with just F1 multiplied by 1. When I equals 2, I'll be left with M1 multiplied by 1. And when Fi equals 3, I'll be left with F2 times 1. And all these other terms would have been multiplied by a 0. So I can find a final form of a vector matrix problem, which is the same form that I found when I used the principle of minimum potential energy method. You might ask yourself, why have these two different methods if they both end up with the same form of the algebraic equation? The reason we did this was because we were going through different ways of deriving the finite element methods. Remember, when the direct method, I ended up with a very similar form, except I couldn't account for distributed loads. Remember that Wx is my distributed load. The reason to derive the principal minimum potential energy method is just because it was a method, a way of getting to this form back when we were thinking in terms of having to have some understanding about the physics behind our problem. The Galerkin's method allows us to just have knowledge of our differential equation. I don't have to think about the physics. I don't have to think about potential energy. If I have a differential equation and I have the boundary values, then I can derive this method. All right? So we've now derived 3 different ways to get this equation. In our next lecture, we will actually use this form, use these various methods on some sample problems.